All right, so today we're going to start talking about inner products, length, and orthogonality. And I'm hoping this will be pretty straightforward. Um, Definitely so if you've had physics, Calc 3. Even if you haven't, it should be pretty straightforward. So if U and V are vectors in Rn, then we can think of them as n by 1 matrices, right? We've been probably doing this all along. So you have your n by 1 column vector. That means that U transpose is what dimensions? Nice. Thank you, Dibs, for that. What are the dimensions of the U transpose? I got 1 by n from Gerald and Megumi and Ben and others. Good. So U transpose is a 1 by n matrix, and the product U transpose times V is what dimensions? That's 1 by 1. It's a 1 by n by an n by 1. So you're just going to get a little 1 by 1 matrix, which is a funny way of looking at a scalar. So we can write this as a real number without brackets. So if you wanted, you could think about it like a 1 by 1 matrix. Imagine you had like the number 1. It's a 1 by 1. It's a very boring matrix. And you're like, this is crazy. That's an awful lot of writing to just write the number 1. So we're just going to write the number 1, which is kind of nice. So it's a real number without brackets. And we're going to call U transpose V the inner product of U and V. It's also written as U dot V. And what do we call U dot V? What kind of product? The dot product. Good. So in case you're missing this, we have inner product is the same as the dot product, at least for our purposes. There's other types of inner products, but as far as matrices are concerned, it really is that simple. Dot was so yesterday, inner is in today. All right. So just to make sure you're tracking, so your inner product is going to take the row, dot it with the column, and to do that, you're going to find a whole bunch of these little teeny products that you can add up. And presumably, you've all done this, or almost everyone's done this in the past. If you haven't had Calc 3 or physics, then maybe the dot product is new to you. If that's the case, that's just fine. Don't stress. This is okay. Maybe for those of you that have had a lot of dot product stuff, like what are the important things to know about the dot product? I've got that it's easy. Okay, so dot product is easy, so don't stress about it. What else do we know about the dot product? What about, so I've got parallel. What about parallel? So yeah, so from Ben, the dot product is about the angle between two lines or between two vectors. Yeah, there's this other product called the cross product that's not as easy. From Evan, the dot product gives a scalar. From Ben, it's kind of like a shadow in a way. It helps us figure out projections. I think that's what you're getting at, Ben. And vector projections, and that's going to be a big deal later on in this chapter. So good. When is the dot product 0? So the dot product is 0 whenever the two vectors we're looking at are perpendicular to each other. So it's maximized when they're parallel. It's 0 when they're perpendicular to each other. Good. All right. So if we want to compute u dot v and v dot u, this would be like saying u dot v in our new world would be the same as u transpose v, which would be 2, -3, 4, multiplied by -4, 2, 1. Here's the blue one. Here's the green one. And you multiply the entries and corresponding entries in sum. And so you're going to get, I think, -10. Yeah. And it would be -10 inside the brackets, but we're going to save ourselves a little bit of writing and skip those brackets. What happens if I go the other way? If I have v dot u, am I going to get a different answer or same answer? Or? I've got a 10, same. I think we mean -10. Yeah, so same result, whichever order. Ahmed asked, is there a difference between scalars and a 1-by-1 matrix? Yes, but we can sort of go back. Maybe you could think about it as they're isomorphic between each other. Ahmed, have you done any programming somewhere in your past? Haven't done programming. Trying to think. Maybe I could do it by analogy. So you could think about this this blue vector here as being you could think about it as being a row vector or a matrix that has only one row. So is it a row vector? Is it a matrix? It's sort of kind of both, but they're also kind of different things. So we can think about it either as a row vector or as a matrix, depending upon what's convenient to us. And so similarly, we could think about -10 as being a 1-by-1 matrix or just a scalar, sort of depending upon what the context or what was convenient to us. They're not quite the same thing, but there's enough similarity that we can fluidly go back and forth. Does that make sense? And again, specifically in the notes, what I'm doing is I'm giving you some permission. So I'm giving you permission to write that 1-by-1 matrix without brackets. And so you think about the times when you're in an assessment and I'm asking you questions. I'm like, well, do you need to write it this way or that way? And you're like, oh, snap. I didn't realize that was important. And right here, I'm giving you permission to write this one as just a number. All right. So theorem, nice friendly theorem. It says that the dot product is kind of sort of our friend. First of all, it says that the order doesn't matter. Secondly, it says that you can distribute across addition. So u plus v dot w would be the same as u dot w plus v dot w. And then the third part tells us that we can associate. So you can have the C with the U, you could have the C out front, you could have the C with the V. So you can move scalars anywhere you want within a dot product. And lastly, we have that if you take a vector and you dot it with itself, so notice if you take a vector u and you dot it with itself, then your answer will always be non-negative. When is it going to be 0? It's going to be 0 when, well, I guess it says right there, if and only if u is equal to 0. Sorry. Right, because in general, it would be when they're perpendicular, but in this case, we're going to be 0. I want to point out that the 0 that's here, that this 0 is a scalar. And that would be if and only if u equals 0, and this is the vector 0. Yeah. Thank you for that, Evan, Ratana, and Sammy. Any questions so far? All right. I want to point something out on this in this next little statement. Here, when I have C1 U1 plus dot 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 plus CP UP, what else did we call that? Like elsewhere in this class, we've given this a name. Pythagorean's too complicated. This is like a linear algebra name. So from Ben, this is a linear combination. And so we have here a linear combination of the u vectors dotted with the w. And what you'll notice is that you're going to end up with sort of like a linear combination of dot products. So we could find that whole linear combination and then dot the result with the w, or we have the choice. We could do a whole bunch of individual dot products, and yeah, we could do a whole bunch of individual dot products. Okay, so it's just kind of a reminder notation thing. It's going to come up later on. All right. In other classes, we would talk about the length of a vector. The word length is so yesterday. Just like dot was yesterday, length is yesterday. Now we talk about the norm of a vector. What is that? It's just the length. If you're like, wow, that is not enough names for the same thing, you could also call this the magnitude of the vector. So is it the length of the vector? Is it the norm of the vector? Is it the magnitude of the vector? It depends on what you want. I think that for those of you that are Phineas and Ferb fans, I think we say that this is the norm of the vector in recognition of Dr. Doofenshmirtz's robot norm. Anyway, the length or norm of V is the non-negative scalar V defined by magnitude of V, and it's the square root of the vector dotted with itself, or the square root of the sum of the squares of the entries. And you'll notice that the magnitude squared is just V dot V. In R2, this is essentially which theorem? And I think somebody already mentioned it. Maybe Abed already mentioned it. This is the Pythagorean theorem. Do you guys know anything about Pythagoras? So he's dead. You probably knew that. Pythagoras, he's dead. He's a Greek guy. He lived like, oh my gosh, I want to say like 350 years BC, somewhere in that world. And he did a whole bunch of things. Apparently he was fixed on triangles. But he kind of sort of started a math cult, like a religion around math. And maybe you've heard this story, but One of the things about the Pythagoreans, that was his cult, was that they did not believe in irrational numbers. Irrational numbers. Those are numbers that can't be written as a fraction of integers. So they didn't believe in irrational numbers. And so there was, the tradition has it, we don't have YouTube footage of this to prove it's true, but tradition has it that one of the members of the Pythagoreans proved that the square root of 2 is irrational. And so they were having this giant party on a boat, and they pushed the guy overboard and drowned him because he proved that square root of 2 is irrational. To me, that seems like kind of an irrational response to that proof, but I don't know. Anyway, so don't say that there's no violence or controversy in math. There definitely is, at least 2,300 years ago, one time. So, all right. So basically, this is the Pythagorean theorem, but now it's generalized to n dimensions. What a note about the notation, that here I have c being a scalar and I have v being a vector. And so if I want to take the norm or find the length or find the magnitude of CV, that would be the absolute value of C times the norm of V. And so, oops, this one's a norm. This one's a traditional absolute value. And so what I'm trying to point out is the absolute value just has one set of bars, but the norm has two sets of bars. Now, I always thought this was cool. I was like, ooh, if you were wanting to take if you're wanting to work with numbers, then you would use absolute value with one bar. And if you're working with vectors, then you would use two bars. And so then if we wanted to find the absolute value of a matrix, we should use 3 bars. So I was like, we should do 3 bars if we wanted to find the absolute value of a matrix. And then maybe if you had a tensor, I think that's like a 3-dimensional matrix, then you would have some 4 bars. But I tried doing this and it worked and it made sense to me, but basically nobody else does it. So I tried to invent my own math notation and mostly I got rejected. I think because eventually people are just like, it just looks like a whole bunch of lines up and down after a while and it doesn't really make any sense to people. So anyway, if you think it's cool, you can adopt it and you can take credit for it too. Simple, important, familiar concept. A vector whose length is 1 is called what kind of vector? A unit vector. Called a unit vector because we think like 1 unit. If we divide a non-zero vector v by its length, that is, we multiply by 1 over the magnitude, of v, we get a unit vector in the same direction as v, and this is called normalizing a vector. So when you normalize a vector, when you shrink it down to length 1, and we'll do an example of that below. So here in example 2, I've got v equal to 5, 2, 4, negative 2. I want to find a unit vector in the same direction as v. That is, I want to normalize v. So to do that, we need the magnitude of v. This is going to be the square root of 5 squared plus 2 squared plus 4 squared plus negative 2 squared which is a funny way of saying square root of 49, I think. Which is pretty close to 7. And so we're looking for a unit vector u. And so our unit vector u will be v divided by the magnitude of v, or I'm just going to put the 1 over 7 out front. 5, 2, 4, negative 2. So let's see if we could tie this back to a linear algebra concept. So let W be a subspace of R2 spanned by X equal to 3/4 negative 2. And I want to find a unit vector basis for W. So first of all, what is the dimension of W? What's the dimension of W? Evan and Alex, it's just 1. Yeah. Why is it 1? Because this is a funny way of saying that W is equal to the span of 3/4 negative 2. If W is equal to the span of 3/4 negative 2, there's one linearly independent vector that spans the whole thing. So the dimensions will be 1. All right. So now we already have a basis. The basis is 3/4 negative 2. But we're asked to find a unit vector basis. So in order to do that, we need to find a unit vector parallel to x. So we need the magnitude of x, square root of 3/4 squared plus negative 2 squared which I've got like square root of 73 over 16. So a unit vector basis is x over the magnitude of x, or this would be 4 over root 73 times 3/4 negative 2. I feel like this is straightforward, but give me a thumbs up if you're doing okay. Okay, lots of thumbs up. Sweet. All right. This particular example is kind of sort of boring, but it gives you a hint of where we're going. So finding a unit basis. So notice dot products or inner products are nice for finding things that are perpendicular. So here we can find unit vectors and we can find when things are perpendicular. And so what we're going to be looking for is combining those things, and we're going to be trying to find a basis that is both orthogonal, perpendicular, and unit, made up of unit bases. So we're going to look for an orthonormal basis. That's where we're kind of going. So this is a pretty boring example. It's an orthonormal basis, but there's only one vector. So that's not very exciting. So how do we find the distance between two numbers on a line? So if you have a number line and you're going from A to B and you want to find the distance, you could say that distance is equal to B minus A, or maybe that's too hard because you're like, well, what if, how do I know which one's A and which one's B, man? Like, that's too hard. And so sometimes we would say that this is equal to the magnitude of B minus A or the magnitude of A minus B. And now it doesn't matter which one you call your A and which one you call your B, because those absolute values take care of the which one comes first issue, right? So that should be kind of sort of familiar. So that's on a number line. More generally, if I have U and V in Rn, then we can talk about the distance between two vectors. I'm going to write that as the distance of U comma V, and it's just the length of the vector U minus V, or the norm of U minus V, or the magnitude of U minus V. Pretty straightforward in 2 dimensions. So here I've got some U vector that's over there, and I got a V vector 3, 2 that's here. And so U minus V would be, U minus V is this vector here or there, because it doesn't matter where the order is. And so all we're looking for is the length of that vector. So U minus V would be like 7, 1 minus 3, 2. Notice I'm using parentheses, not angle brackets, not brackets. I'm just using parentheses here for my vectors. Get 4 minus 1. And the magnitude of U minus V is the magnitude of 4 comma minus 1, which is the square root of 4 squared plus negative 1 squared, or 17, or the root of 17. Here's what's a little weird about that. Like, this should be super familiar. It's a funny way of writing it, but what do we just use? Like, at some level, I just used, people type in, like, what old formulas? Yeah, I used our old friend Pythag. Or maybe you recognize that this was also the distance formula. Yeah, from Evan, yeah. So this is kind of familiar. But what's a little bit interesting about this formula is that it applies more broadly. Did I skip something? Oh. So this can actually apply in 3 dimensions, 4 dimensions, 5 dimensions, whatever. So if I want to find the formula for the distance between two vectors in 3D, now the distance from U to V is going to be the magnitude of U minus V, or the square root of U1 minus V1 squared plus U2, oops. This is Bono's favorite vector. Right. It's just the Pythagorean theorem, but now with 3 components instead of 2 components. And the crazy part is you could do this for 10 dimensions. So like, what does distance mean between two 10-dimensional vectors? I don't know, but we can calculate it. Like, and if you think about what vectors could represent, like this is just a little bit bizarre. Think about like Gerald's at the top of my screen. Think about the Gerald vector. Okay. And so the Gerald vector might include his ID number. It might include his birth date. It might include, I'm trying to think what other numbers are there. Like it might include your street address. It might include your GPA. It might include the total number of credits. Okay, so we have the Gerald vector, and then on my screen, Teresa's next, and she's got some vector. Like, we could literally figure out what's the distance between Gerald and Teresa. I don't know what that means or what that represents, but you could have these 10-dimensional vectors with all these bizarre components. And from a mathematical standpoint, we could just multiply these entries together and square them and sum them all up, and we would get a number that doesn't have a lot of meaning or significance, but it does get you this idea that we could talk about distance in an arbitrary set of dimensions, which is pretty whacked out. All right. Gerald and Teresa, you're off the hook. So two vectors u and v in Rn are orthogonal to each other if u dot v equals 0. My way of saying this is that the dot product or the inner product eats perpendicular things for lunch. Just chews them up and spits out 0. Super, super helpful. Yeah, your social, yeah, all those things, craziness. Okay. Two vectors u and v are orthogonal if and only if the Pythagorean theorem holds. So this is kind of interesting. So they're orthogonal if their dot product is 0. They're also orthogonal if and only if the Pythagorean theorem holds. And just in case you're missing it, this is like your hypotenuse. Here's your a squared, and here's your b squared. So this would be like saying the magnitude of u, magnitude of v, and this would be magnitude of u plus v. And I need something like that. All right, so remember where I said we're going. We're going towards this orthonormal basis. That's kind of where we're headed. So we've got the idea of normalizing a vector, turning them into unit vectors. And now here, we're starting to introduce this idea of orthogonality. It's starting to come into our lesson. So if a vector z is orthogonal to every vector in a subspace W of Rn, then z is said to be orthogonal to W. I'm losing track. Have you guys used the word orthogonal somewhere else? Is that a familiar word to everybody? I think so. So orthogonal is just code for, yeah, it was used in Calc 3. So orthogonal is code for perpendicular. Like perpendicular. Yeah, from Calc 3, probably from physics and other places. So back in high school in Calc 2, you talked about perpendicular things. That was so Calc 2. Now you're cooler than that. Now you say orthogonal. The set of all these orthogonal vectors to W is called the orthogonal complement of W and is denoted with W perp. So it's called the orthogonal or perpendicular complement of W and is denoted W perp. This thing right here is red. And you might say, wait a second, I've watched crime shows. I know perp means like perpetrator. Like this W, this is like an evil, vile thing. We got to arrest it. Nope, this is a different kind of W. So this would be W perpendicular. So we call it W perp, short for W perpendicular, short for the orthogonal component of W, et cetera, et cetera. Holy shnikes, that was a lot. Let me end by just showing you pictures, and then we'll come back to this tomorrow. So when we talk about W perp, we're saying that you have a space like this. This would be your W. And then W perp would be all the stuff that's perpendicular to that space. Or down below, if you called, if for example, I called this one my W, then everything that's perpendicular to the purple line, now that one would be my perpendicular subspace. So they're like spaces that are perpendicular to each other. And we'll talk more about this later. But again, it's going to be helpful as we work towards this orthonormal basis, which is our middle step towards getting us towards that general least squares method. I'd like to start with this example 6 to try to help you have a visual for what's going on with these perpendicular subspaces. So we're going to let W be a plane through the origin in R3. So here's that W plane. And let L be the line through the origin and perpendicular to W. So please note that they're perpendicular to each other. If Z and W are non-zero, let's see if we can figure out where those are. So here's our Z vector right here. And here is our V vector there. Okay. So if, wait, Z, I said W. I lost my W, sorry. Did I read? It's not a V, it's a W. Sorry, I covered that up. Sorry, my Z is along the purple line if my W is on the plane. So if Z is on L and W is on W, then the line segment from 0 to Z is perpendicular to the line segment from 0 to W. That is Z dot W equals 0. See the figure. So each vector on L is orthogonal to every vector in W. In fact, L consists of all vectors that are orthogonal to the W's in W. And W consists of all the vectors orthogonal to the Z's in Z. So let me erase the picture and let me make so you can see it again. So we have two subspaces. So we have a subspace W down here that is a plane. And on that plane, there's a whole bunch of points, and we'll call those points W's. And then we have a line, and our line we're going to call L. And there are points on the line or vectors on the line that we'll call Z. And so what we want you to notice is that every possible red W on the plane is perpendicular to every possible z, purple z on the line. So yeah, so you end up with this z dot w equals 0. And so what this gives us is that the L, the purple L, is the part of W, it's perpendicular to W. And W, the space, is perpendicular to our L. So these are perpendicular subspaces. Okay. And once again, we would read this notation. We would read this as L perp, short for the subspace that is perpendicular to L. Questions so far? So a vector x is in W perp if and only if x is orthogonal to every vector in a set that spans W. So it's in W perp if it's orthogonal to everything that's in W. And then we also have that W perp is a subspace of Rn. So you have here the W is a subspace. And you also have the W perp is a subspace. And so we can look at an example of this, and I think I have some details to work through later. But we commented briefly that the null space and the row space are essentially orthogonal to each other. And so if you have your null space here, and then your row space would be perpendicular to it. Or I guess you could say it something like the null space of A perp would be equal to the row space of A. Similarly, you could get that. You may remember that stuff about the null space of A transpose. So the null space of A transpose is perpendicular to the column space. Yeah. So again, what is this saying? It's saying that every vector in the null space is perpendicular to every vector in the row space, or every vector in the column space is perpendicular to every vector in the null space of A transpose. What's our tool that helps us to verify that vectors are perpendicular? It's actually not if and only if. Yeah, the dot product. If implies that U and V are equal to 0. u dot v equals 0. Is this an if and only if statement? Like, what's the issue around if and only if here? So it could be 0, for, like Ben said, it could be 0 in other circumstances, and Gerald pulled it out. If v or u was 0, then the dot product would be also 0. So if we could say, maybe we could add and say non-zero uv are perpendicular if and only if u dot v equals 0. So as long as we specify that they're non-zero, then we can get an if and only if statement out of it. So the next theorem basically just says in words what the picture does. So it says, let A be an M by N matrix. The orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. So this theorem here is saying the same thing as those pictures up above. Questions? All right, so let's use the null space and row space from example 5 back from section 4.5 or 4.6 to check that random vectors from each are orthogonal to each other. So I just want to sort of verify. I'm guessing you probably don't have example 5 from that old section memorized, so I took the liberty of screenshotting it to remind you of what was going on. So what we're trying to show is that the null space and row space are perpendicular to each other. And so we're going to grab some arbitrary vectors. So can I get some like small numbers that you like numbers between -2 and 2 that are all integers? What are your favorite numbers? I got 1, so I've got a 1 and a 1. So I'll use that first. So if you imagine that we focused in on this null space here, and so we took one of the first vector, and we just pulled this out of thin air, 3, 4, 1, 0, 0, plus 1. You gave me the 1, so we just are grabbing things that are nice. -4, 5, 2, 0, 1. And that will equal, looks like -1, 9, 3, 0, 1. Does that make sense? So this is, what is this? This thing is I'm going to call it random. It's not really random. We just picked it up, but just like, it's just a vector in null A. So then we'll look over at the purple stuff, and I need 3 random numbers from the purple side. For the purple side, what are 3 nice numbers? I got 1 and 2, and I need another random number. 2, 4. How about 2, 4, and 1? Let's do it. So we've got 2, and now I know this sounds weird, but I'm going to treat them like they're column vectors. So I've got 1, 0, -3, 0, 4. So I changed my row into a column for the sake of the exercise. Plus 4 times 0, 1, -4, 0, -5, plus 1. Again, where did the 2, 4, 1 come from? You just gave me random numbers to work with. Okay. I think I've got 2, 4. negative 22, 0, 14. Anybody want, can somebody verify that I did okay? Is this a the 0, not 0. 0 should be 1. Oh, right here. Is that right? Now am I good? Cool. Thank you for correcting. It would make a difference. Okay, so what did we just find? We have here, this right here is a vector in the row space of A. And so now let's dot them and see what happens. So if we take -1, 9, 3, 0, 1, and we dot it with 2, 4, -22, 1, -14. It's actually always kind of scary to just let you guys pick random numbers. Let's see if it works. So I've got -2 plus 36 minus 66 plus 0 minus 14. There's no way that's 0. Looking at my notes, trying to figure out, anybody see the error? Should be 0. There's a problem. What I can see, give me a second. It should, the row basis I think is okay. It should be from the row reduced. So the question from, suggestion from Dibs is that could the row basis be from the original columns? It should be from the rows of the row reduced matrix. Okay, I think my purple's right. I think there's a problem in my green. I think that there's a problem. I'm just like comparing notes to what I have written here. And I think that there's a problem in my green null basis. So let's go back. I think I made a mistake. I think there might be a mistake here. So can you just verify that I've got the right? Oh, I can't erase because that's actually a screenshot. Can you verify the null space? The 2 in the vector 2 be in row 4. So right here from Richard, he's asking a question here. Anybody else? He's saying it should be. So I should have my 1s in column where my free variable columns are, in column 3, in column 5, right? Oh my gosh, I feel like I'm losing it. Felix agrees with Richard. So what should these green ones be? Let's just go back. Let's do it that way. Need space. So we should have 3, 4, and then -4, 5, 0, 2, 1. That's my second one. And then my first one is supposed to be what? Sorry, I'm just like too close to it. the same. 3, 4, 1, 0, 0. Does that look right? Getting your notes right? I'm just too close to it to see it at the moment. Cool. Okay, let me just double check to make sure now my notes line up. Cool. I think that's right. And I'm saying that because it now matches my previous notes. So let's check. How does that change things? So we're saying, hey, we made a mistake on our null space. That's so terrible. We actually caught it somewhere else. Caught it. So that's going to change this this vector right here to be -4, 5, 0, 2, 1, which is going to change our potential null space vector to be what, -1, 9, 1, 2, 1. Thank you, Ben. Which means we can check like that, which means our whole thing, first couple, should now be -2 plus 36 minus 22 plus 2 minus, which is a very funny way of saying zero. Woohoo. Wow, I didn't expect to find an error, but we just found an error from our notes from what, 2 or 3 weeks ago. So I will try to send out a note in Slack with the exact page number of where that error was from before. It's kind of funny. Questions about that? Cool. All right. One last little thing in this section. I want to show that the dot product is equal to the magnitude of u times the magnitude of v times the cosine of v, where v is the angle between the two vectors, using the law of cosines. And so I have a little picture here. And I want to kind of remember what these various things are. So if we have the if I focus in on, or if I go from this line here, okay. Do people understand that this is the law of cosines? Let me start there. Does everybody see that as the law of cosines? Okay, good. So that's the law of cosines. So let's move things around a little bit. So this is telling me that 2 magnitude of u times the magnitude of v times the cosine of v is equal to the magnitude of u squared plus the magnitude of v squared minus the magnitude of u minus v squared. Just all I did was I solved for that one, that side right there. Okay. So now we got to break up these magnitudes. They're just a little bit hard for us. And so this first one here, so that one would be equal to u dot u plus magnitude of v squared would be v dot v minus, and then the orange one will be u minus v dotted with u minus v. All right, so let's mess around with this orange stuff for a second. So this orange stuff would be the same thing as u dot u minus u dot v plus v dot u plus v dot v. What can you tell me about u dot v and v dot u? They are the same because you have commutativity for the dot product. So those guys are the same. So I have a minus u dot v and a positive v dot u. So those are going to cancel each other out. So this is equal to, no. Thank you, Dib. Sorry, this is apparently not my day. Thank you, Dibs. Sorry, they're both minus. Oh my gosh, Dusty. Wake up. What did you have for breakfast? Okay, so this is equal to, we have here a u dot u minus a u dot u. So those two will cancel out. So I'm going to have a 0 plus, then we have a v dot v minus a v dot v. So that's also going to be a 0. And then I have a minus, and then I've got 2 of those u dot v. So this will be plus 2 u dot v. And I think that's the 2 that Gerline pointed out a 2, and I think this is the 2 that she was thinking I was missing. So what are we saying? We're saying that 2 magnitude of u, magnitude of v, cosine v is equal to 2 u dot v, which would be the same thing as telling us what we want to show, that u dot v equals magnitude of u times the magnitude of v times the cosine of the angle between u and v. Okay. So what's the point of this? The point of this is, I think, that we verified the dot product, the relationship between the dot product and the law of cosines. So I think it's kind of easy to lose track of what we were working on in this particular section. So what we did in this particular section is we were focused on 3 things. We were focused on the inner product. That's our new name for the dot product. We were focused on length. Length, that's the same as magnitude or norm, just the length of a vector, pretty easy to find. And then thirdly, we were talking about orthogonality. That's just our fancy word for saying perpendicular.